This video is going to talk about a couple key theorems in calculus. Now, we've already talked about one a few units back called the Intermediate Value Theorem, and I'll review that in the beginning of this video in just a couple moments. But the main purpose of this video is to talk about a new theorem called the Mean Value Theorem. In calculus, it's going to be important to figure out when the slope of the secant line is equal to the slope of the tangent line. Or in other words, when does the average rate of change equal the instantaneous rate of change? And if that happens, some key things can sort of exist within the function at that point. And so we're trying to find a way to guarantee if that's going to happen in certain cases. So the mean value theorem guarantees the existence of a time when that actually happens, when the slope of the secant equals the slope of the tangent. When iPass was first invented, people were afraid that they'd actually get more traffic tickets. The transponder checks in at various toll booths along the tollway. And if you arrive at the next toll booth too soon, then the mean value theorem would suggest that you must have been traveling above the speed limit at some time during your trip. So that's kind of what the mean value theorem is going to guarantee. It guarantees the existence of a derivative value. So with that background, let me talk first about the intermediate value theorem and just kind of review how that worked. And without maybe doing a very formal example, I'll share with you just, or remind you kind of how this theorem comes together. So remember that the intermediate value theorem, or IVT for short, states that if your function is continuous on an interval, then, and we also have betweenness of some sort of element in question, then the IVT will guarantee the existence of that value. For example, look at number one. Does function g have a 0 on the interval between 4 and 7? So if you look at 4 and 7, I have an output of 9 and then an output of 2. If I just go on those with those points, I can't guarantee. But if you look at this, I actually hit a negative output here at g of 6. So I might say something like, yes, this will be guaranteed. And we have to state that g is continuous. By the way, how do we know g is continuous? The function g is differentiable, and differentiability implies continuity. So I can say that g is in fact continuous. And then I can say that g of 6 is less than 0. 0 is the element in question, and that is less than g of 4. So I'm using the interval from 4 to 6, which is within the overall interval of 4 to 7. I could say, therefore, by IVT, there exists a value x equals, and often we'll use the variable c, x equals c, such that f of c, f of c equals 0. There we go. So an IVT proof. Question 2 says, will g of x ever equal 6.75? So that's my element in question. And yet again, let's see if I can figure out an interval where that might happen. So 6.75 would exist between 9 and 3, so between these two outputs, meaning between g of 4 and g of 4.5, IVT would guarantee the existence of a c value where the function is equal to 6.75. So today, though, in this video, what I'd like to share with you is what the mean value theorem states and kind of what it represents. And I like this image. You see a function in red, and then I have a secant line that's connecting f of a and f of b. So that there's the secant line. The slope of that secant line would be the average rate of change. So f of b minus f of a divided by b minus a. And then up above here, we have a point between a and b where I can draw a tangent line, and I can construct that tangent line so that it is perfectly parallel to the secant line, meaning that it has the same slope as the secant line, and therefore the derivative, slope of the tangent line, equals the average rate of change, slope of the secant line. Now, in symbols, what does that mean? Well, down here in this rectangle, we'll just write out the sort of the conclusion of MVT. So you can read the hypothesis here. And essentially, it guarantees the existence of a value on the derivative. So we'll call that value f prime of c, and that would be my derivative that is equal to the slope of the tangent or equal to the average rate. Average rate of change is f of b minus f of a divided by b minus a. That's the conclusion of the mean value theorem. And notice the prerequisites. We have to make sure that the function that we're analyzing is defined and continuous on the closed interval a to b, and it's differentiable on the open interval from a to b. So continuity must be proved or shown, and then differentiability must also be shown. If that happens, then we can actually apply the MVT, and we guarantee the existence of this derivative value. In words, if the conditions are met, again, the slope of the tangent equals the slope of the secant. So that's the mean value theorem, and I'll show you a couple examples in this video on how that works. There's one special case of the mean value theorem, and it happens when f of a and f of b are equal. And if that happens, then the numerator of my average rate of change essentially is 0, meaning the derivative must also be 0. We call this Rolle's theorem. So Rolle's theorem, just a special case of MVT. So f prime of c, stylus is skipping around today, pardon me for that. F prime of c is equal to f of b minus f of a divided by b minus a. But if f of b and f of a are the same number, then my numerator and overall difference quotient is going to equal 0. So that's Rolle's theorem. And in words, we might say that Rolle's theorem would guarantee the existence of a derivative value on the interval which has a horizontal tangent, because the slope, or the derivative, slope of the secant and slope of the tangent is equal to 0. Now, one last note here. If one of the c values, if one of the values on the interval that you discover is actually an endpoint of the interval, we have to reject it. MVT will only guarantee the existence of a derivative in between the endpoints, so on an open interval. So if I write this down, c value must exist on the open interval from a to b. So if we end up discovering that the c value is an endpoint, we will just discard it, we will reject it, and not use that as part of the MVT conclusion. So to kind of wrap this up here, I've got the conditions on the left. Continuous, f must be continuous, f must be differentiable. Notice the difference between the closed interval for continuity and then the open interval for differentiability. And then in words and symbols, you can see the conclusion for the mean value theorem. So how does this look, and how might this appear in some kind of problem or homework question, maybe a test question? So on the next slide over here, let me walk you through a couple examples. By the way, just to kind of summarize the three theorems that we now have talked about in calculus, IVT guarantees the existence of a function value, so we can match that one with choice B. MVT, mean value theorem, guarantees the existence of a derivative value. And then Rolle's theorem, again, just that special case of MVT where the slope of the secant and tangent are both 0. So the existence of the derivative value would be 0. So match up those theorems. And here I have now a numerical example where I'm hoping to apply our knowledge of these theorems. And the table here is given as, looks like the velocity of a car every 5 seconds over a period of 50 seconds. And so then I have these statements below the table. And what I want us to do in this video is just to kind of see which statements are true, which theorems would support the statements, and we'll kind of make note of that on the far right-hand column where we list the theorem. So to begin, let's look at statement number 1. Statement 1 says that at some time between 0 and 5 seconds, the acceleration must be 4 miles per hour squared. And by the way, notice that the table is a velocity table. So we're dealing with the function that is velocity. Well, acceleration, if I start with that word, that's the derivative of velocity. So I'm basically seeking to guarantee the existence of a derivative value. It kind of sounds like mean value theorem. I'll probably be using MVT to prove that. Same thing with statement 4, acceleration. Statement 5, acceleration. So those are the derivatives of velocity. And if we're proving the existence of a value there, think about using MVT or Rolle's theorem. So for statement 1, let's take a look at the interval from 0 to 5. So if I'm checking acceleration, the average acceleration between 0 and 5 would be v of 5 minus v of 0 divided by 5 minus 0, or 20 divided by 5, and that equals 4. So if the average rate of change is equal to 4, MVT will basically guarantee the existence that the derivative, or the acceleration, must be exactly 4 miles per hour squared in that time interval. So that's going to be a true statement by using MVT. Okay. Statement 2, at some time between 0 and 5 seconds, the velocity must be 10. Now we're back to just verifying the existence of velocity. So that would be just a function value. If I look at 0 and 5, v of 0 and v of 5 goes from 0 to 20, and 10 miles per hour would fit in between. So I have continuity with velocity, and I have between this. That's an IVT proof. So I would say yes, I can verify that by the intermediate value theorem. Statement 3, from 0 to 50, the velocity must be 70 miles per hour. And notice the interval here. It's between 0 and 50. At time 50, velocity is 70. But if you notice, nowhere between 0 and 50 do I have any evidence that the velocity hit 70, not until that endpoint. So technically, I have no way to guarantee that statement. Let's look at 4. At some time between 10 and 15 seconds, the acceleration must be blank miles per hour squared. Well, let's figure that out. So v of 15 minus v of 10 divided by 15 minus 10. That looks to be 45 minus 30 divided by 15 minus 10, or 5. So 15 over 5 would be 3. So I'll put a 3 right there in the blank. And by the mean value theorem, I can prove, I just showed right there, the difference coefficient equal to 3. I can prove that there must have been a time when the acceleration was exactly 3 miles per hour squared. And then finally this, at some time, and the times aren't given here for the interval, the acceleration must be 0. Well, what I want to do is figure out what kind of function outputs would generate a 0 in the numerator of my difference quotient. So basically, where would f of b and f of a be the same? Or in this case, where are my velocities going to be the same? And I think there's a couple different places. I'll pick these two maybe right here where I see a 60 and then another 60. So between the time of 25 and 40 seconds, if I did an average rate of change, I would find out that the acceleration would be exactly 0. So I'll say 25 and 40 seconds. The acceleration must be 0. That's Rolle's theorem. Rolle's theorem is just a special case of the mean value theorem when I have a derivative value that is exactly equal to 0. And then finally this, that was a numerical example using a table of values. Let me close the video by showing you an algebraic example. So this problem says, if possible, find the number in the given interval that satisfies the conclusion of the MVT, of the mean value theorem. Well, if we're going to use MVT, or basically prove that we can do so, let's make sure that this function is continuous and also differentiable. So it's a polynomial. So yes, it's continuous because f of x is a polynomial, and polynomials are continuous. Is it differentiable? Yes, f prime of x is equal to 2x minus 5, so the derivative also exists. I have continuity, I have differentiability, so MVT applies. Now let's see if I can actually use it to find that C value. Notice the interval is between -1 and 3. So let's find the slope of the tangent and equate that with the slope of the secant. Slope of the secant is simply average rate of change. So the interval here will be f of 3 minus f of -1 divided by 3 minus -1. And I believe that computes to a value of -3. You can check that. There's the slope of the secant. The slope of the tangent is just the derivative, so f prime. F prime. Well, f prime of x is 2x minus 5. My power rule there, so I'll replace that with a c, so 2c minus 5. And I'll equate that to the slope of the secant. Let's solve for c. 2c is equal to 2. My c value is going to be 1. Let's make sure that that c value is in between the interval, -1 to 3, and it is. So then I can claim that there must be a time MVT guarantees the existence of a value. In this case, that time or that value is actually c equals 1, where the slope of the secant is equal to the slope of the tangent. The average rate of change is equal to the instantaneous rate of change. And then again, just add that note, make sure that the value you discover, the value that you find, is in that open interval a to b. If c is equal to the endpoint a or endpoint b, we have to reject it. So c cannot be equal to a or b. So that is the mean value theorem, along with Rolle's theorem. We saw a numerical example and also an algebraic example. And what you'll see is MVT being applied to a number of free response questions and even multiple choice questions in your AP exam. So practice and make sure that you understand kind of both the hypothesis to MVT and also what it guarantees. I hope that video was helpful to you, and good luck with your practice on MVT, IVT, and Rolle's theorem.